So yeah, thank you for inviting me to this section. And I've been working on Kepler now at Unfolded for quite a bit of 3 years. Kepler for 2 years and Unfolded for about a year. And I've been giving talks about Kepler for quite a long time, but this is the first time I actually get to give a talk when I'm sitting on my couch. So hopefully, I'll be more relaxed and give you more backdoor stories about how we make this application. So today I want to go over some of the interesting findings when we are working on Kepler and how general learnings we did when we started to tackle this task of developing a large-scale geospatial analytic toolset specifically for data, urban data, and so on and so forth. And a little bit about myself. I studied architecture, the actual architecture about building design, not software architecture. So I studied architecture for about 9 years, and then I transitioned myself into software engineering. The reason being, I know architecture is all about designing spaces and physical object, but I also very interested in playing with digits, something I don't have to always build with my hand. And then combining those two passions of self-engineering and spatial design, I find my best fits as being geospatial data visualization. I worked at Uber for about 5 years, I think since 2014. And then I was the first person on Uber's data visualization team, so it has been quite a ride. And during my time at Uber, I open sourced a software called Kepler.gl. It's the tool we built internally, specific for visualizing large-scale geospatial data. And because it has been used widely, we open source it as a way to contribute back to the community. And about 6 months to a year ago, I ended my Uber journey. I took Kepler.gl, and together with the main architect behind Deck.gl and H3, we started a company called Unfolded. So yeah, so that's the history. It's all written, and my interest, although I'm trained as an architect, I was trained to thinking about spatial design and specifically, how how people interact with physical space. But on the other side, I think that's quite close to when you're thinking about visualizing spatial data, because more and more spatial data, we're also talking about how we better understand space from people's movement. So I think those two backgrounds kind of bring me to where I am today. And it's a very unique, I think from my previous background in architecture, I actually get quite interesting insight when I was thinking about urban data and how to better visualize it and what kind of insight it can give us. So when it comes to geospatial data, more and more, we're not just talking about the physical space anymore. And if you're talking about 10 or 20 years ago, when you're thinking about GIS, it's all about coastal lines, about building footprint, about contours and typography. But today, when we talk about geospatial data, we're actually talking a lot about, GPS points, people's movement, birds' movement, anything that related to things that can move. So, movement data has been a very big thing when I joined Uber, and also basically the whole, Uber's business built upon. So coming from a traditional GIS understanding, tackling the new domain of movement data has become a challenge for us, especially for the quantity of data that came in every day, and for the type of data that's no longer static, it's moving, it's three-dimensional. How can we better tackle the space using our traditional technology, and how can we do innovation around that? It's something we have been working into. So, this is giving you a scale of the data we're dealing with every day when we were at Uber. This is 1 day of trip in London, just probably before COVID. And this is I think this in 2016. If you have thousands, 100,000s of trips every day just running on your platform, and then every single trip you're collecting hundreds of millions of pings, and then those all contain information as extremely valuable for us to better run the business, to provide a better experience. So we're taking on the task at the visualization team to build not just a pretty animation, but actually understand what is behind this moving data. So what do we do with visualization and why are we using it? So when you're looking at just this image, you probably think about it's some street network of certain cities. Yes, it is red. It is probably using some kind of binning technique. Yes, you're right. But what actually are we binning here? When we're looking at this map, we're actually using just the GPS pings, the raw GPS pings that we're collecting on drivers' phones. And because when you take a ride, we know we are tracking drivers' phones to give you a better experience. Also in terms of safety. So just by visualizing the raw aggregation of pings, we can already see a network of road because that's where the car tends to drive. And then if you want to look deeper into it, you can, this map actually has 3-dimension into it. We can see where, even the altitude of the cars are at. So with an image like this, it's obviously still just an image, but we were able to give it to our data science where they dig into every single pins. It can help us understanding where some of the places that people are, fraudulent behavior happening. If they are faking the ride, then we'll be able to catch them with this kind of anomaly detection, running anomaly detection on a, binning maps like this. Another interesting view when we're looking at this is, when you're talking about trips, it's all about origin and destinations. So the traditional visualization method doesn't really give you us a bit, good lenses of how things are connected. So this is using a 1-day trip of London, and we are just looking at the connection of 2 points, the start and end of the trips. This obviously millions of trips will come together. We'll be able to draw this kind of explosion type of style of viz, where you can see the different part of urban centers are kind of connected to each other. You can see the small hubs are just in the suburb of London, and how that kind of impact, how that give you a better understanding how road and network connect different part of the city. And another one we did when we looking at this is we use 1 day of taxi trips when we're trying to test our platform. We use 1 day of taxi trip in New York. We aggregate them into a hexagonal bin. We add the 3D dimension to it to see the density of trips. And then you can see areas like this immediately stand out because this is where the airport is. And then, Upper East Side and Brooklyn. So by adding 3D dimension to to a density map, we have a much better lenses to see where the actual anomaly is. It gets us more information than just looking at the colors. So then we're not just looking at 3-dimensional, we also have this idea, because we're looking at moving things. So we started to explore how can we look at moving trips, but also adding, valuable information to it. So this is a visualization we did when we tried to compare traffic of Uber trips and separate trips and versus traffics of pooling trips. So when you take pools, you obviously, 2 people sharing 1 car versus when you do separate trips, you have 2 cars. So we were able to calculate the actual traffic volume in these 2 different scenarios and then project the volume back to each individual trips using color to signify the actual traffic density on different road segments and then make this animation. So, by combining different techniques, visualization can actually help us immediately see the difference between the traffics to see whether, having riding Uber pool versus, not running report have an impact on the city's road network. So, with visualization, obviously with the things I just saw, you just see it, we turn all the millions of data points into something that actually you can see what's behind the data. So that has been like, my career for the first 2 years, almost two years of when I was at Uber. I did millions of these type of maps. All of them are using hundreds of millions of data points. I was exploring different ways to build this type of visualization that can get you see through the points and digits and then find some insights behind that. So, obviously design meaningful visualization requires a lot of try and error. And then, sometimes I would spend weeks just tweaking one visualization, trying to use other, different techniques to see how can I best expose the information behind it. In real world, it's really like something like, you almost never succeed at first try. You spend hours just to debug your code. And even when you finally seeing something on the screen, you almost never see immediately the things you're looking for. So there are a lot of try and error go into it, and it takes really long time for each individual person just to do that. And let alone the skill set you have to acquire, in terms of design, in terms of coding, in terms of using all different tools. So kind of that's why I built Kepler.gl. So, with Kepler.gl, we can give our data science a tool to fast explore, to visual explore of millions of geospatial data in the browser. I like to say that, as a designer, I like to do individual maps. I like to, create beautiful things. But as a software engineer, I actually like to create software that replaces myself. So, I don't have to do a map for 2 weeks to give it to you. Anyone, a data science, a data analyst can use my tool to create maps. So much about job security, but in other sense, developing tools on platform will give people whatever and then you will have them kind of equip them with the skill sets of an individual software engineer, but I have them, multiply yourself to have anyone to be able to make insightful maps. So that's a background behind Kepler. And then, Kepler is open sourced by Uber in 2018. It's now donated into Linux Foundation. It's open under the Urban Computing Foundation. So, audience here, it's a old browser based. You don't have to use any installation. You just go to Kepler.gl in the browser. You can drag your file into it. It has a lot of presets for you. So, you can handle large data sets. So anything that, be around 100,000 to 1 million rows of data, we can easily handle in the browser without any backend. It's a pure client-side, meaning that data is not uploaded anywhere. It stays in your browser, and it's built on top of WebGL so that we can visualize millions of data points without any delay. And then it has a lot of precise visualization layer. Those are the layers I have been using when I was doing, transportation-based, urban data-based visualization, and I think will be useful to people. And obviously, it gives you a quick explore to apply filters and interactions, and then it adds like 3D to the maps, because when we're talking about urban data, a 3D view is important. And then it does on-the-fly geo-aggregation. So a lot of steps, so I will go through some of them. The typical process of doing spatial visualization is you collect data, you do some processing, you use visualization techniques, mainly do visual encoding, and then you create different visualizations, pick one that you think that is most informative. So we're using Kepler.gl. We try to consolidate all this process into one tool, one easy, quick tool for people to do quick analysis. Right. So the flow is very simple. You upload some data sets. You can apply filters or not, which usually give you a lot of interaction to dig behind the data, and then you use a different set of layers that we provide you. Those layers will be enough for you to almost to do most of the geoanalytics, and then you can interact with it in the browser as quick explore, seeing what's behind it, and so on and so forth. So a typical workflow will be, you go to Kepler.gl, you drag a file into it, it uploads, and then because Kepler.gl detect what's in the what geodata is in it, usually we'll be able to draw a quick, already generate a layer for you, and then you can do the quick visual explore of applying different color scales, quantile, quantize, square roots, and then you can add filters to it. You can add even looking at map in the different 3D views, zoom in and zoom out. So those are very quick explorations that you can do inside just one tool. And usually this type of visualization is usually people spend just about 10 to 20 minutes using Kepler.gl. They will be able to create any maps that usually will take hours to make. So because we're building on top of WebGL, a lot of things we do is how to interact with the data in the browser. Traditionally, if you use tools as QGIS or even ArcGIS, almost all the maps you generate as statics. QGIS nowadays have been going quite along, so you will be able to do some interaction. But this is our tool is in the browser, so it renders in with your own computer's GPU. It allows you to do this kind of quick brush interactions and adding, aggregating into hexabins or grids, filter them, and doing time animation if you have a time dimension, and then adding 3 dimension to any type of polygon or spatial data. So all of those are built into the tool, and then quite interactive and performative. So this is a generic version of Kepler.gl. But generally, because the challenges we have, the large scale of data we have at Uber, we built this tool for in-browser exploration. So because no one, not all software engineer knows how to do geospatial analysis, and now not all data science knows how to code. So we try to bring a tool that can bridge all these gaps. So anyone like a PM or designer can use this to do quick analysis. So here I want to talk more deeper into the findings when we're building this tool, and then some of the techniques we use, or some of the things that we're facing that's quite interesting when we're going into it. So the first thing I want to talk about is large scale data sets, and that's basically the whole power behind Kepler.gl is that you were able to visualizing millions of data points in the browser. So for us to handle large scale data set in the browser, we use the GPU rendering. What does that really mean when I keep talking about GPU? So I just learned that not everyone actually understands the GPU computing we keep referring is not some kind of backend that Kepler.gl ran, in the side of the earth, that our backend is using GPU, so you send data to us and we're processing it. So when we're talking about GPU computation, we are actually talking about everyone's computer has a GPU. You show something on the screen, what renders that? It's your GPU. So we're using your own computer's power, GPU power, to render those data in the browser. To do that, Kepler is built on top of Deck.gl. It's another layer of framework that we open source at the Uber's visualization team. So Deck.gl is all about WebGL powered visualizations. So when you compare the two techniques we traditionally use and nowadays we use, so your computer has CPU, your computer has GPU. The difference between CPU and GPU is that CPU is a central processing unit, as it kind of implied, which means CPU is extremely powerful. Sometimes you have 8 core or 12 16 core CPU. All of the pipes is one single thread. So when you give it a command, the CPU will calculate for you, and you wait on the other side to get the result. Versus GPU, that GPU is known for parallel processing because it's rendering each single pixels on your screen. So you can think about GPU as this giant motherboard with thousands of little this microprocessors. So each processor calculate a pixel or calculate a shape on your screen. And then it's not, each of this processor is not as powerful as a CPU, but each of the processor can do the exact same calculation, but in a parallel process manner. This will make it extremely useful for visualization. Why? Because visualization is all about converting a data points into a pixels on your screen. So, we can utilize the power of GPU where we have GPU calculate on every single point, and we calculate and all those little formulas we put into each visual processor will run in parallel, and the end result is the colors and positions on your screen. So that's the that's the basic understanding of how GPU can help in the visualization concept. So some of the actual language that you tell GPU to run this command called GLSL shaders. And this is something that Deck.gl is capable of. Kepler also uses GLS shaders to do a lot of GPU real-time interactions. So an example of using GPU to do real-time interactions is something like brushing, right? So if you think about what brushing is actually do, brushing is where when you move your mouse, you basically apply a filter to the million arcs you have on the screen. This filter will filter the arcs based on the proximity of them to your mouse. If we have this calculation in CPU, you can imagine a long thread of each thread. Each time the mouse move, you will call the CPU to say, filter this a million points for me. And then you will have to do it multiple times, 30 seconds, 30 frames per second when your mouse move around the map. But if you can do this calculation in GPU, it's actually then just same as when you are just rendering those arcs, because we tell the GPU to say, hey, take the input, this is my input. Each single arc goes through each single GPU processor, and we tell them to say, hey, take the mouse position and tell me whether this arc I should render it or not. So this is how we can use GPU to accelerate interactions on your screen without have to do, with the capacity of handling millions of points. The filter on Kepler, so the time animation is actually also done in GPU, where we in real time animating 1 million points. This all smoothly renders on your screen. That's how it can become really fast when you are doing this type of animation. And the second thing we're designing Kepler.gl is we have a lot of interesting visualization type when we're trying to do it, because those are the things that specifically targeting urban movement data. So the traditional, visualization or geospatial visualization, you are mostly using scatter plot, chloroplasts for polygons and shapes, and heat maps for density. When we go beyond the traditional CPU rendering, or we add, GPU rendering to the sense, we can do a lot more than just the traditional visualization types. In Kepler.gl, we have these 3D arcs layer, we have the 3D binding layer, and then also the moving trips layer. Just giving the technique we have, we will be able to use these type of layer to handle large scale movement data. So, the 3D arc layer is something that a specific useful for understanding origin destinations. You will be able to see in a 3-dimensional how one thing moves from one part to another, and then these all renders with the 3D arc layer. Another layer we come with is the trip animation layer. So this is very useful for visualizing any kind of space, moving units in space. So this is a map I did visualizing just using these, blue sky network data, looking at, I think it was called open sky sensors data, visualizing the positions of airplanes flying across oceans. So, each of the plane has this one trail, and then using the trip layer, you'll be able to animate a single dot flowing through these trails all in one tool. And the third concept we're constantly dealing with is adding a discrete global grid system to our visualization. So, when you're just looking at the raw data, something like this, a million points, what can you really get out of it besides a nice, pretty, dark night scale of map that's showing what density is? So when we come to handling, actually understanding millions of raw points, we really need to use a certain kind of grid system to help us project points into a unified shape and then calculate measures inside each speed shape. So, to better understand raw points data, we're using a grid system called H3. So H3 is a hexagonal hierarchy spatial indexing system. So basically, if you think about the Earth as a sphere, we want to have a way to be able to divide the sphere into different resolution of unified shape, and use that as the basic and geometric shape to understanding the raw input data. So that's what H3 is. H3 is a hexagon shape, and there's many studies into why hexagon shape is better than, say, a grid shape or a spherical shape. So I will not go too deep into it, but long story short, using hexagon, it's extremely fast to be able to correlate with the neighbors. Geometry is also extremely fast to be able to go between different resolutions and aggregate or break down between them. So sometimes one of the maps we usually do is that we'll be able to aggregate each individual, all the raw trips inside one city into a hexagon grid about 50 meters, and then using different metrics, visualizing different metrics by aggregating just inside those different 50-meter hexagon unit. So after doing that, you will be able to convert the raw points into any level or resolution of hexagons, and then calculating metrics between that. So those three maps we did is when we're looking at New York City, all the trips in New York City, we will be able to look at in aggregating, looking at I hate to say this word, heterogeneity. It's a way to say, whether the trips happens in this unit is mostly a single same destination trips, or it's a multi-destination trips. It's a way for us to better understanding whether this trip is mostly taken by local or mostly taken by tourists. And then we also, looking at this metric, looking at ETA metrics, where we understand different part of the city might have, longer ETA, and why is that? And we're also using this looking at average trip distance, and so one all the way on the right. We want to see whether certain parts of the city specifically have longer distance trips. In this case, in New York, you will see the tip of New York actually has people take. You cannot see my mouse. So the tip of New York is where the financial district is. Usually people take longer trip from that because it's harder to get around to other part of the New York from there. So we'll be able to use this grid system, applying different metrics to review these insights. Without a unified grid system, just by looking at points, it's impossible to get this level of findings. So another interesting study, we using the grid system together with machine learning, is that we looked at trips that taken inside downtown San Francisco. But instead of just looking at a single metric, we are looking at, for each cells, we're looking at the trip per hour and then to see whether there's a way we can categorize these cell movements. A better way to explaining is that, if this cell locating in financial district, you will probably see a higher surge of trips in the morning and in the rush hour, evening rush hour. But if this cell is in, say, a theater district or entertainment district, you'll be able to see only able to see a high level of trips after 6 p.m. So, just looking at drawing this graph of different cells, we'll be able to use a machine learning algorithm to categorize these cells, and then, almost just extrapolate them from each other, and then seeing that, different parts of the city have different part of movement. I usually call this like the pulse of movement map. And then, going back to urban study, where we're actually looking at the district planning map of San Francisco on the right, it's very direct. You can see, just by looking at travel patterns, we can immediately reflect back on the district planning map of why those traffic pattern happens. Because the certain area is planned as financial district and certain area is planned as a residential area. I mean, obviously compare it is the obvious first thing to do, but you can imagine this will go much deeper into feed the data back into the actual urban study or the urban planners, saying that, hey, you plan for this area to be the financial district, or you plan to have this area to have lower traffic volumes. But here we give you the data to tell you whether this actually happens, right? So, if you think about the traditional urban study, the only way people be able to collect data like this is through some kind of surveys, or, putting 1 or 2 sensors at the road or a different road network to sense the traffic volumes. But with this kind of discrete collecting of data, even with people unaware of way of collecting data, we can have a much realistic drawing of what actually happens in the cities. So, wow, time's flying fast. I should go a little faster, but we just going to just get to the fun part. So, obviously, when it comes to motion and movement, a big part of it is about understanding time. And traditional GIS maps usually dealing with things that never moves, like buildings, rivers, mountains. The movement of those data almost, you don't really have to think about exactly how things change and how fast things change. But when we're dealing with movement data, we actually have to look into different type of understanding time. So time could be continuous, time could be discrete when you are projecting them different buckets, or time can come in the interval by intervals case. And sometimes when you ask a question, you're no longer just ask when it happens. You also ask when and how long it happens. So to be able to answering all these questions just about time, we are facing an extremely hard challenge, because spatial temporal data is something that we will have to use visualization, and with some kind of movement and with some kind of coloring scale, we have to be able to help people understand when and where for how long. All those things that come together in just one tool has become an extremely big challenge for us. So, for example, when it comes to discrete way of treating time, it's kind of the easy case, where you have a bunch of points, let's say the trip, a bunch of where the trip starts, and you have all the points, each of the points come with one time stamp. So trip A happens at 9 a.m., trip 10 happens at 10 a.m. So if those are the discrete time scenario, the most easier way to examine that is you just filter them. You filter them by time. So something like this, it's a very direct way of using discrete way of visualizing particles. So these are the Mapbox, some engineer did this visualization using NOAA data, looking at satellite imagery sensors of wind speed during a hurricane. I think that's Hurricane Sandy, or one of the hurricanes in US. There are many of them. One of the bigger ones. So by just looking at each individual particle and the speed or vector of that specific particle, we will be able to visualizing the movement throughout time of how wind, how hurricane and the wind speed interact in this case. So this is the easy part where I just do filter them by time. But not everything is discrete. Sometimes we're dealing with continuous changes. Like for example, a trip is something, a car moving is example where you have just one car. This car is at point A, 10 a.m., point B at 11 p.m. For when we're dealing with a continuous movement, we have to use a different way of visualizing it. That's why we create this layer called trip layer. We group things by a unique ID, and then we visualize the movement of it by drawing a path and having the particle moving along that path. So this is the, in this case, we're no longer dealing with discrete points. We're actually dealing with a object moving through a path. So if for us to visualize that is the use of trip layer. And then obviously there's still the case of how you're handling intervals, how you're handling not just when and where, and when and where for how long. And those are the cases that we are working on. There are new layers coming out to be able to handle that. That's like can predict what's coming along. So in the end is the part of my favorite part where when I was working on this tool, I realized how important just to have some movement on your visualization will tell stories of it, and then just be able to have people to interact with the slider, interact with a filter, or interact with brushings to see things moving and changing on the map will actually give you a much better insights versus if everything comes in static. So that's why when we are designing this tool, we are very adamant about there should be no static image. Every interaction should be able to be continuous. Like if you're changing a filter, you should allow them to drag things to see changes. You are changing opacity, you should be able to allow people to drag the slider to see how colors change. And all the little details will have to be interactive, will have to be responsive. So when someone are setting it, exploring it, they will be, even just by looking at the feedback of their actions, they will be finding something more useful and insightful. So for example, when we did this, we added this kind of drawing functionality. So partially drawing, partially filtering. The idea is that when you draw a specific area and use it as the filter, you'll be able to filter all the layers throughout this entire map. So by just moving this little square on the map, you will be able to see where other layers have changed based on the result of the current layer you're filtering. In this case, for example, I'm looking at the pickup and drop off points, they're color different. So when I filter on my pickup layer, I will be able to see, all the points that's all the trips that starting in my little square but ended in somewhere else, right? So, this is basically another way of brushing, but in a 2D dimensional, having a more precise dimension. So, crossing layer filtering, well as dragging along, give you the instant feedback of your action and see how things changes when you are filtering around different part of the city. And last but not least, when we're doing this tools, we know that there's a lot of other tools around there people are using, and they are using it for not just understanding spatial data, they're using for understanding abstract data that does not have location points, right? People using Tableau to do most of the analytics, but then inside Tableau, sometimes they also want to draw layers. Or people using Jupyter notebooks to do most of the data processing, but at the same time, they want to be able to use to do draw maps. So when we did Kepler, we know that it's not just going to be a standalone application, but you can able to embed it in any kind of the tools. So we have Kepler for Jupyter, we have Kepler for Tableau, It's also something that you can build web application with it. So you can build any like a dashboard with Kepler being just part of the map visualization tools. So yeah, that's part about it. And behind Kepler, we're using different web standard web development libraries. Some of them we open source, some of them are pretty commonly used, like React and MapGL. And open source is a big thing when we were at Uber. So all the libraries we use to build Kepler.gl, we also open source it for people to be able to benefit on this idea of WebGL-based large-scale visualization frameworks. And then obviously building an open source community is fun. You put your tool out there, and then constantly I monitor Twitter to see whether any exciting maps people created. If they hashtag Kepler, I will be able to notify. And it's extremely fruitful when I see people that's not from transportation domain using this tool, like environmental studies, even architecture, and people, logistic industry. I see many different type of use cases coming along. They kind of solidify the idea of, geospatial data is not just about moving cars, but it's also about environmental studies and people's movement. So yeah, so we end up winning the Information is Beautiful award, and it's kind of, it works more now because this award has been going on for yearly for about 5 or 6 years, and be able to win. And I was in school when I was monitoring with the Information is Beautiful award, and I ended up winning it through my work at Uber, through my work at Kepler. That it's a big solidify of changing from one design domain into another. So what's next? We have very fast going through. So after working on Kepler for many years, couple of folks at Uber, when we were working on open source softwares, we decided to start a company together called Unfolded. So the reason we started is because we realized, Kepler is a visualization part. The visualization brings everything you see, but there's still a lot more you need to do even before you bring your data into Kepler. So, to better understanding geospatial data, you need to run your own H3 library. You need to run your own backend. It could be anything, and data might come in different formats. So we realized just using Kepler is not enough to have the full scale of, from the part you collect the data to the part you get insights. So that's why us come together saying, let's just take the things we already work on for many years, let's put them together to see if we can build anything that's, build something that challenge traditional way of people understanding spatial data science. So, that's a background story behind Kepler, behind Unfolded. And then a couple of highlight is that, we want to tackle spatial unification using H3. We want to tackle an all-in-one platform, and we want to everything GPU based, right? So we are taking this strengths of each of our core libraries and putting them together to build a new company. So spatial unification is the biggest thing we want to tackle. This is definitely not something that just Kepler itself can do. When it comes to spatial unification, the story is that you might have data in satellite imagery, you might have data in point cloud, you might have data in bitmaps, and you might have spatial data come in many different formats. So traditionally the way of handling that is merely drawing layers on top of each other, but be able to break through the layers, consolidate data into one specific unit is extremely hard. Which H3, we believe we'll be able to handle that. So we can do this kind of map by breaking down taking data from Earth Engine's satellite imagery database, and then project them into H3 cells and drawing this vector-based map inside Kepler. So this is turning the satellite imagery map into a vector-based interactive map in the browser. So every single pixel you see is drawn with a H3 cell. And then with that, you go beyond the traditional static image. You can actually dig into each cell of those of these H3 hexagons, looking at the different matches behind there. And going one level beyond, this is something where they're trying to use the hexagonal aggregation so that we take this is a map showing the social demographic of US counties. So we be able to take the population data of that counties and then drawing the hexagons based on whether this part of the country actually has people, or whether this part of or doesn't have it. So be able to filter down the cells based on population. So this map is much closer reflection of your social demographic than something like a color pass, for example. So those are the techniques we're playing. And then another one we did is that we be able to take, I think, 8 million of farm parcels, break them into this hexagonal tiling. So this is not just hexagons in one data table. This is about building vector tiles using hexagons. So we're able to draw this map smoothly, interactive into different layers. So it's hosted on our website, so I don't have time to go into it. But those are some techniques we're playing around with our new marriage of H3, Kepler, and Deck.gl. So the product we're trying to launch is called Unfolded Studio. And at the get-go, it's very similar. It's basically built on top of Kepler, which is open source tool, and then connecting it with H3 backend to do data unification, spatial enrichment, and transformation. So it's not launched yet. So, but if you're interested, just stay tuned and hear more news coming out from Unfolded. We're our company built by software engineers, so we're very eager to open source. We're very eager to helping academic and building different interesting projects, right? So yeah, so that's what I have to say, and happy to take more questions and follow Unfolded on Twitter.
Thank you, Shan. I mean, that was a really fascinating and brilliant presentation. Your work is really amazing, I would say. But yeah, so well, we would have had a big round of applause now, but unfortunately, this virtual setting just doesn't allow to it. But yeah, so virtually applauding you. So yeah, again, for the Q&A session, we will be using the chat. Okay, so there are already quite a lot of questions. If anyone wants to join the conversation, I mean, you're all able to mute yourself. If not, I will read the questions. So I don't know, Alex, there's, well, first questions is from, well, two questions actually from Alex. In case you want to jump in, feel free. But yeah, okay, so question one. So conceptually, do you see a difference between geographic analysis and geographic visualizations as the tools blur these boundaries? This is the first question.
That's an interesting question. So, I can say that I started from the visualization side of things, obviously. So, I starting from taking the already result of analysis and turn them into pixels or visualizations. And as I was coming from that direction, I realized that, sometimes color and shapes is just not enough to allow you to provide deeper insights. So I kind of, from Kepler.gl, when I built, people usually say that it's like a Photoshop for maps. When I built Kepler.gl, I started to talk with people who are using the tool, like my favorite person, Sina Kashuk, now become my co-founder, is one person. He is from a deep analysis background. So he will be able to tell me that, we not just want to see layers, we actually want to see how, these different metrics interact with each other. But it's also on your map. So you have a map, but I want to see how this metric changes your maps. That's a part of analysis he wants to do. Or I have another person come to me saying that, hey, I have this, hexagon layer, and then I have this point layer, I have this polygon layer, but how do I project points through hexagons into polygons? So those are the things that usually analysis and that people from analytic background were, wanted to do. And then I realized just from visualization, they won't be able to do that. So, I will say that as I try to blur the boundary as much as I can by learning from people who are doing those analysis. And part of doing the tool is usually, most of those analysis, like breaking down geospatial transformation, people used to do that with code. And with code is that you write a code, you get a result, you do it, you show it in visualization. There's always a long, workflow. But if I will be able to build more and more of those analysis capacity using the toolset I'm most comfortable with, or more powerful, like for example, I will be able to convert those, projection into GPU shaders, then I will give you a much faster experience doing those explorations. So I will be able to absorb more and more traditional analytic methods into my front-end tools using the more powerful calculation there. But obviously, I'm not trying to be ambitious doing everything on the visualization platform. I don't, Kepler is known to be easy to use, and I do not intend to do a QGIS in browser. So, I will say that we want to build a tool more focusing on the new type of geospatial data that deal with movement. We want to be able to focusing on something that, dealing with the GPS point, dealing with satellite imagery, the type of data that's, not handled well by the traditional technology. So I think that's our opportunities are, and that's why, more excites us, like the founders of Unfolded. And we want to be more focusing on innovation versus, bringing every single QGIS command into Kepler.
Thanks. So there's another question from Alex. I noticed a few references to climate data in your new company's newsfeed. Are you planning some raster-friendly tools?
Sorry,
are you planning to develop some raster-friendly tools? So working with raster data as well.
So that's an interesting question because we think all raster are vectors. So when you put it on the screen, rasters become pixels. So, the project we did with Indigo Act is, hexagonal binning tiling is actually a visually raster map, but actually drawing by, vector pixels of hexagons. So we want to be able, obviously we want to be able to treat rasters, but we think that all raster can be turning into pixels and can be turning into something you dig into every single pixels and get information out of it. And that's why we built this hexagon tiling system to specifically handle the raster tile use cases.
Okay, thanks. So there's another question from Dani. Do you have tools or plan to make Kepler easy to work with data that is not fully loaded? For example, in cases where your data is too large, and so loading only chunks of a table, or streaming just aggregations, for example, H3 binning for points while reading rather than directly from memory.
Yeah, so part of it is already there. So, currently our hexagon binning is not based on H3, but we have a PR out actually adding H3 binning to our hexagon layer. So, you load points and it bins into H3, but we also handle the directly loading H3. So if your data contains H3 ID, drop it into Kepler, it's going to render as hexagons. And then in terms of loading incomplete, so this is always a challenge there. So part of the things we're trying to handle at Unfolded is that we're actually building this tiling backend, this partial of the backend we're building, where we convert the data into vector tiles, and then front-end Kepler will be able to in real time load those piece by piece based on where your map zooming is. Then obviously, there's the part of being open source and not open source is that everything open source has to be only work in browser. we cannot open source any backend because, we have to run a cloud, we have to run something that, Google will charge us for or AWS will charge us for, and people will not also be comfortable just uploading data to any kind of open backend. So, at Unfolded, what we're trying to do is that we actually help you to build this backend yourself. So, haven't really nailed down the plan obviously yet, but we realize the whole, whole level of interaction comes from being able to have something like a H3 backed backend will help you break down boundaries, geotransforming all there, and then loading it incrementally on inside the Kepler as a front end. So I hope that answers the question.
Cool. Barry Bragg asks, has there been discussion at Unfolded about integrating the H3 indexing system with distributed key value stores such as HBase for query and storage of geospatial data, similar to how the GeoMe's and GeoWave frameworks do using space filling curves?
Yeah, that's a very technical question. So the answer is yes, but we are doing something. I wouldn't say we were actually building it. So part of the Unfold is literally build up all the different backend integrations so that Kepler works on the front end, but we have many type of different backend integrations. So there's a very long list of things we're trying to do. Top of the list will be a vector tiling, H3 tiling, PostGIS, and Snowflakes, all the commonly used industrial and Google data, BigQuery, all the commonly used geospatial query or backend storage. We haven't really given stars in the GeoMe's yet because it's kind of down the line, but we will get there when a customer comes to us saying that our data is in Sparks, our data is in using Databricks. Figure out how to integrating that, then we'll have to handle that. Right now it's already going down the list, and then whenever a request comes, we're adding another integration. By the way, we only have 10 people at the company, so we're not we're not like 100 people company that can just do these things overnight.
But you say you did integrate with BigQuery as well.
Yeah, internally we're already
Yeah. Okay, that's good. And there's another question again by Barry Bragg. Has Kepler.gl looked at the possibility of integrating the FlowMapGL layer from Teralytics, which is built on Back.gl as a layer type?
Yes, so the one interesting thing about Kepler.gl donating to Urban Computing Foundation is that I'm the chair of the technical advisory on Urban Computing Foundation, and FlowMapGL is in the process of also being donated to UCF, and everything under this open source hood, meaning that FlowMapGL is built on top of Deck, and then FlowMapGL will be very easy to go into Kepler, and then we'll be the developer come to Ilya Boyadin, the FlowMapGL developer, come to us UCF saying that we want to donating it. The first thing he asks is, can I bring this into Kepler? So the answer is obviously yes, and then we'll be happy family under the GL hood. So you will see that in Kepler very soon.
Great. So a question from Jean Juan. It's about he's an R user. Actually, I would have asked the same at a certain point, and he's a bit jealous of the Jupyter integration that Python users have. So does the Kepler.gl team have plans for supporting more programming languages for platforms in the future? So there's any plan for any integration with R as well?
R, wow, R is
asking you additional job.
So yeah, I can program in Python, JavaScript, C. R is not something I'm familiar with. I think the short answer is probably not, because the reason we'll be able to build Jupyter for Jupyter integration is because Jupyter itself has this widget library that we can use to build a Kepler widget. I don't think that widget library that Jupyter provide has our language support. So, that will be a big limitation factor for us.
Okay, thanks. Yeah, this is not good news, but yeah.
I'm sorry, might just jump in. I think it's just a good opportunity for me to start learning Python for using Kepler.
Great.
Good. Okay, so well, there are comments that stress how brilliant and interesting your presentation was just to report it. And then so another comment from Jay. I want to be sure to say thank you for leading this remarkable project. I love the visualizations that Kepler creates and appreciate your sharing your work with the world. Then a question now from Robin. So although Kepler.gl is great at analyzing, visualizing in-memory data, are you considering a way to bind it to already stored data, be it shared with something like Apache Arrow or in a distance and fast database management system? And again, thanks a lot for your presentation. It was enlightening.
Yeah, so the answer is yes. The short answer is unfolded. So obviously we realized that the reason we actually want a background story why we quit Uber and started this company is we want to expand use of DAG Kepler beyond the current the whatever backend system Uber has. We know there's a lot of requests coming from of different backend integrations, but if we at Uber, there's no incentive for us to actually take on those integration challenges. So, or to actually working on those. So, but starting with Unfolded, we want to expose Kepler to not just the Uber itself as a company, but also many different companies that has the requirement to understand visualizing geospatial data. And part of the opportunity there is really build up this different backend integrations with anything that's on the market. And we are tackling down the list, as I said, one by one. And obviously there are, exciting things we can do on the front, like vector tile support, like hexagons, hex tiling, bitmap, central image, a lot of things we can tackle on the front. There's also a lot of things we can tackle on the back, meaning going down the list of, different spatial databases, have them smoothly taken into by Unfolded Studio, which is, basically a container for Kepler.gl. So very challenging task. If you're interested in joining, let me know. We're hiring. If you have any,
I think it would be great though, because we
were hiring, so I forgot to throw out there too. And because of the COVID situation, remote friendly.
Okay, good to know. So okay, so another question from Bob Barr. So what are the requirements for the browser platform for Kepler.gl, if any? And well, clearly both the power of the GPUs and available memory, presumably both GPUs and host machine, will affect what can be done.
Yeah, so that's like a very good question. So obviously WebGL, so your browser has, if you go to WebGL, better WebGL 2. So you just go to see whether your browser support WebGL 2. That's what I'll tell you. So basically all modern browsers, anything that's, Chrome, Firefox, Safari, probably not IE, but IE is not good for anything. So newer IE will also support WebGL, but be able to do more. Where we go into WebGL tool, you want like probably Chrome or Firefox, right? So this is something that you immediately know whether you can run Kepler. And on the GPU side, I will say, almost all modern laptop computer, if you have a gaming computer, even better. But like I have a MacBook Pro, it works fine. If you have a MacBook Air, maybe a little trickier, but if you just have, slightly good laptop, desktop is always great. So you will be able to use Kepler. It's the hardware part is actually not very strict. And obviously you can go crazy on it. You can buy, your map, the whole map cylinder computer, that would be great. But usually, no, it's the boundary is really not your GPU capacity, it's how much browser allow you to upload. So that's actually the bottleneck there.
Thanks. Okay, so question from Seo Park. Where do you put importance between backend and frontend only for your role in Unfolded? So
where do I put importance?
Yeah, probably when do you invest more or of your effort, I would say, in the back end and front end in your role? Yeah.
So right now, I would say we are still mostly investing in front end just because our lead, me, I'm good at front end. And backend part, we're really just investigating. We're really working on the fun part, actually. We are really interested in how do we build any backend with H3 and how do we do different type of data unification with H3. And we are starting to building up more, I will say, target backend team should just do data integrations where, different using more core resources on the front end and unification, more kind of innovation side, and then we're building up another kind of backend team that just purely doing integration. Right now it's really client based, so whoever bring us a request first, we work on that.
Okay, thanks. So again, comments about your excellent work and people thanking you. Again, Casper Hugh says, I'd like to say thank you for all these projects. They've given me a lot of joy and a lot of head scratching learning React. Looking forward to Unfolded Studio. And then he has also a question. Is there any plan to have the option for Cartesian coordinate system in Kepler.gl? Or does this drift away from the geospatial origins? I have begun using data-agnostic for graph visualization and think it would be very powerful.
Yeah, we did a globe. So we actually, data-agnostic just added the globe projection. So this is something we put in our website immediately. So other projection system right now, not really in the plan because, still we render on top of Mapbox, or, WebMarketer. Once we move into more abstract visualization, we will be able to do, just without just XYZ without any geo coordinates. I think most of the time when people come with us with a different projection system, we just tell them to convert it with QGIS and then upload. So it's it's not a priority, and it will be fun to have it eventually. But right now we're not thinking about it. Besides the globe.
Okay, thanks. Fair enough. I would say already quite a lot of stuff. So Bernardo Luyero asking, do you plan on allowing converting Polygon data to a H3 grid in the browser, like population counts from census sector, for example? Would you do that, maybe generating random points in the census sectors and counting these, or calculating it via area intersection or some other ways? I think this also relates with the possibility of integrating data with Unfolded, right?
Yes, the answer is yes. This is something that we're trying to tackle. This is basically, our core thing. We're trying to figure it out. And obviously, front end, we will do it in front end, but at a certain point, you just can't do things in front end anymore if you have, say, 1 terabyte of data. We will also provide, we were working on like a kind of front end back end hybrid solution where, we will have, if you have less than, a couple 100,000 million points, we can do it in front end. But if you have bigger ones, we will give you like APIs, or using FOD Studio. Behind FOD Studio is a data processing part. Then we will give you some kind of UI for you to do that before you transform those data into H3 and then pull them up in Studio. So that's the two ways we're gonna do, because we know we cannot just build everything in front end. It's not fair to your computer. It's also not a good use of our resources. We started a company knowing that we will have to build some kind of backend performance, backend support for this unification things we're trying to tackle.
Thanks. So again, Barry Bragg, another think sort of more backhand question. So is there the possibility of adding a WFS data loader to Kepler.gl for retrieval of GeoJSON CSV data over OGC services?
WKT or W what?
WFS.
Yeah, I heard about that request.
Yeah, it's a very kind of geography like kind of format.
Whenever I go to this talks, there's always feature requests, and for me, it's more like if we see one thing we did the survey is really, if we see this being requested many times, we will consider it as high priority. So right now, I don't see many people asking for WFS, and I also think there are already tools that can convert that into anything like GeoJSON that we support. So not a priority, but if you was sign up and be a customer, we will probably we will do it.
Okay, good. Fair enough again. So, yeah, people thanking you, fantastic presentations. Let's see if there's any other questions specifically. Not really. I mean, if I may, I would add another. I had a few actually, but I noticed that you were already kind of overwhelmed with questions. But I had a question more, sort of conceptual like question, because what I really appreciate of your work is also that is really beautiful, and it's something that sometimes in the balance between beauty and meanings, researchers or data analysts generally tend to be more inclined towards meaning, but actually I think that also the aesthetic aspect and making a visualization more catching can actually increase the power of the meaning itself. So I just wanted to ask you, what's your thought about, if you've ever, I think you've thought about it, and the way you actually deal balancing these two elements, the aesthetic aspects and the more meaning insights element.
Yeah, I think that's a fair question, and I would say most of the time I don't have to choose one or another. I think as obviously I'm not like the creative coder type of person, so my first entry point is always building information visualization, right? You first have to show something, and then on top of that, I will add beauty to it. I will have different color scale. I will play around with it. Either I can do it in 3D, and I think for me, it's obviously most important is information, and then on top of that, you can do a very informative ugly map, but then making it look much nicer is not that hard, at least in my point of view. So first you get information out, and then you use different techniques to make it more presentable. I think from my point of view, I always just to do whatever is informative first. I never really thought about I will just do art without care about what's behind that, right? So maybe that's why I switched from architecture to software engineering.
Okay, okay, great. So there's also a kind of reason behind the life choice. So another question that I have that I think might be also relevant for part of our audience is that because we have in the lab several PhD students, probably online some master student now, but also all of us working with geospatial data eventually end up making geospatial visualization. So I wanted to ask you, what do you think, if you have any suggestions, recommendations for those who are getting started with geospatial visualization, if there are some elements that that needed to be mostly taken care of, or also some well, things that you absolutely cannot do, if any. Yeah.
It's yeah, I know I'm not PhD, I did master's. So I think to me it's you know, you really wanted to use the time to learn new things, like try everything out. It usually gives you a more better understanding even of your current tools you're comfortable with. I think a lot of it comes down to, you know, doing, you know, challenge you, go out of your comfort zones. I think for, you know, PhD student, learn coding in fashion like JavaScript, Python, try D3, you know, just equip yourself with a different kind of skill set and then be able to use them in different project and scenarios. I think that's something that I would encourage. I guess I think, you know, for me to be able to come here is like, you know, during one of my, when I was in architecture school, I took a class doing modeling, and then I kind of learned a little bit scripting. It's not even like with any language, you just learn a little bit scripting inside the 3D modeling software to build shapes. And I thought that was pretty cool. So I started to, you know, take a look at different programming languages and started play around with JavaScript D3. And you just get, you know, always keep up to what are people doing, what are the new things coming out, and then, you know, be more informative on your on whatever technology that's out there. It's always a good thing.
Okay, thanks. Thank you very much. Is there any other question or comments from the audience? Not now. I would, yeah, I mean, just for the last few minutes, another aspect that I really think is brilliant about your work for Kepler, but also now in Unfolded, is the fact that it's open sourced, which is really great. And we've been discussions within the lab lately about open science, reproducibility, and open source, our code, and so on. Yeah, it takes additional work probably, but then it's, well, the main idea was that in the end it's quite rewarding. So I just wanted to ask you your experience with that, and what you think about the open source community.
Yeah, I think, you know, a good thing about open sourcing, or it's actually, I think open sourcing is a way to speed up innovation. In a sense, if you do anything closed source, the brain that goes into a software just be a couple of person that's working on it. But if you open source it, obviously you have to go through the hurdle of, all right, everyone's gonna see it, you know, like they're gonna see what's behind it. They realize everything's like, you know, hold up, hangers and duct tapes. But once you go over that hurdle, you know, you have people that probably much better, you know, some people much better than me in React commenting on my code, or I have the, you know, the core Redux developer commenting on my code. So, you know, you will be able to have this much greater audience and help you make the project better, right? So, you know, doing Kepler.gl, we have done many 2 surveys already. Every time we do a survey, we learn a lot of, more expectation. What are the features that people are using? And then also by just looking at how people are using it, like all the different kind of use cases, we'll understand where are the next feature we should build, and where are some of the drawbacks or some of the bugs. Even just like throwing out there so people telling you this is broken, it's still valuable than just having a small group of people using your tool. So those are the things that I think comes together why open source is important to developing good technology. And that being said, on Urban Computing Foundation, if you have anything you want open source, come to me. Having a foundation being there is that we will be able to help you to, so you are not on your own. We'll be help you promote your project, getting the proper open source structure set up, help you organize meetings, and give you advice on how to maintain open source community here and there. So yeah.
Thanks. This is very, very, very good to know. So again, if there's no any other question or comments from the audience, well, I want to thank Shan again. That was really brilliant. Thank you very much. Yeah, thank the audience for also the discussion. I think it was very interesting. It was particularly technical, but it was very, very interesting. Lots of requests for Shan, but yeah, so we will stay tuned to see how unfolded unfold and yeah, and
hopefully we don't fold, but yes.
No, it's like the rolling out of unfold. Yeah.
All right, great.
So and yeah, so watch out for the future events we will have. We have so you can watch our space on Eventbrite. We already have a few events planned, and yeah, we will advertise them on our channels like Twitter and again Eventbrite. So thanks again, Shan. That was really brilliant. And yeah, I mean, I wish you good luck for unfolded. I mean, this seems to be well, it's really promising and it's a brilliant tool